Hello, everyone. This is Dave Card talking to you from Florida. I'm sorry we can't all be together for the conference. It's a great honor for me to be asked to make this presentation. What I'm going to be talking to you about is a practical perspective on software safety. This is based on my experience in actually building software-intensive systems. So the objectives of this presentation are to introduce the system developers to a comprehensive approach to ensuring software quality and safety, and also to help researchers identify some useful topics for further research. Let's begin with the definition of safety. Safety is the condition of being protected from or unlikely to cause danger, risk, or injury. That's just from the dictionary. The typical types of dangers and injuries we have to worry about are financial, physical, and reputational. If we talk specifically about software safety, we need to understand that, first of all, software by itself is generally safe. There are some financial applications, of course, where some damage can be done directly through the software, but generally, systems where software is interacting with hardware can be safe or unsafe, but the software itself is safe. Software can induce failures in the systems by causing the system to not take action when it should, by taking an unintended action or taking an action at the wrong time. Safety cannot really be proven in advance, and software does not wear out. It is delivered with defects. And with hardware systems, the primary concern is failure due to wear. That's not a problem for us, but the problem for software is that we deliver systems with defects already. So software safety is dependent on the quality and the reliability of the system, so we can't really talk about safety without also talking about and addressing quality and reliability. Here's a little model that helps us to think about the issue of software quality, safety, and reliability. We typically go through a software development process which produces a software product which goes into operation, and the consequence of that, the customer gets some benefit. Okay? So when we're talking about software development, the development process and the software product, these can be talked about in terms of process quality and product quality, and that's generally addressed in terms of conformance to standards. And these are static properties. In other words, these are properties that can be observed in the process, that can be observed in the product, and don't necessarily require execution to see. Once the software goes into operation, then we have what we call emergent properties. We have behaviors that cannot be observed in just looking at the static product, at the code itself. And those are things like safety, security, and usability. They're emergent properties. And as a consequence of experiencing these things, the user gets some benefit and they become satisfied, hopefully. So these emergent properties are things that are not observable in the static software. And you cannot really prove them or test them to certainty because they really depend on the environment and how the system is being used. And we often don't know exactly how it's going to be used and exactly what the environment's going to be. And of course, those things can change over time. So I would say it's practically impossible to prove that a system is safe or test it in order to determine that it's completely 100% safe. But of course, we want it to get as close to that as we can. So what do we do in order to manage these emergent properties like safety? Key things that we need to understand the operational context in which the software is operating. Then we need to perform a technical risk analysis. There's been a lot of focus in recent years on project management risk analysis, looking at risk to cost and schedule. And then while that's important, it's not really enough to address safety. We need to look at the technical risks, what can happen to the system itself. Okay, and of course, in order to be able to handle the emergent properties, we have to handle the static properties. So we have to make sure that our static software quality is as good as possible. And then we need to perform usage-based testing, testing based on what the users are planning to do. And this is different from use case testing. Use case testing is really a programming concept. The programmers define use cases and test according to those use cases. Those don't necessarily reflect the full usage, the full operational scenario in which the software is being used. And in hardware systems, because failure is the most common cause of lack of safety, there's a lot of emphasis on redundancy as a solution. Redundancy doesn't work very well in software. It's difficult and expensive to achieve. If you look at something like the space shuttle system, it actually has 5 computers on board. 4 of them are the main flight controllers and the two backup systems, so that if the system fails, it can be another one will plug in automatically. And that's really because of hardware failure. That addresses hardware failure. But the software running on those 4 systems is exactly the same. So to achieve some software redundancy, what NASA did was to have a separate team from the one that developed the first flight control software. A separate team developed independently another flight control piece of software that runs in parallel with the primary flight controllers. And so it gives you a solution that hopefully would not have the same defects in it as the ones in the original program. But that was very expensive. You had to pay twice for developing the software. And in addition, when you're dealing with safety, you need to consider the user and the operator behavior. Most people are familiar with the Deepwater Horizon disaster. But one thing that people don't know that wasn't stressed too much in the reports was that the blowout preventer for several weeks before the disaster was actually giving lots of alarms. So the operators actually turned off all the alarms. Now it turned out that was not a factor in the accident, but in another situation it could have been a factor in an accident. It could have contributed to an accident because the BOP didn't work, but it didn't work for other reasons, not because the alarms were turned off in the case of the Deepwater Horizon. Another example is the 737 MAX. So the 737 MAX, the software, the flight system there could introduce a stall in the aircraft, and then what pilots are trained to do when they experience a stall is to put the nose down. And of course, if you're close to the ground and you put the nose down, you're gonna crash. So the typical operator behavior did not match that problem. It was not appropriate for that problem. So you need to think about those things also in terms of dealing with safety. And what this really means is that you need to take a system-level, comprehensive approach. You need to follow some kind of process that helps you think about all these things. And in my experience, this concept of technology qualification is something that does that. So technology qualification is this process for ensuring that a complex system meets quality, reliability, and safety requirements. There are several different approaches to this that have been documented, and I have some references at the end. The approach that we're going to talk about is one that focuses on innovative technology, because there's a lot of emphasis in software in producing new applications and new software. And one of the things in order to do technology qualification, you have to establish the objectives up front, objectives that are based on the project intent. You may not even have specific users or customers, but you have to understand what is the intent of how the system is going to be used. And then you build your qualification process around that. So here's the 5 steps that we use that I'm going to talk about today that are based on the Emergent Practice A203. The first we call technology assessment, which is what's innovative in the software. We qualified it or verified it or verified it in more detail. And then for those items, we need to identify and or tailor applicable standards, both process standards and product standards that are going to be applied during development. So these are things that happen during the technology assessment part. What are the appropriate standards? And then what's actually new, because we want to focus our attention on the things that are new. Then for the things that are new, we want to do a risk analysis, and that might be a FMITA or FMIA we also identify what we call critical parameters, which are the performance measures that the system has to meet in order to be successful. So if you're talking about, for example, a battery-powered system, then the battery life is a critical parameter. When you run out of battery, the system stops working. And then the next step is the planning, where you have to develop a test plan. You need a data collection plan because you need to collect data during the course of testing and development. And then you need to mitigate risks that have been identified in the risk analysis. And then the fourth step is to do the testing, collect the data, and assess conformance standards during the development and testing. And then the final step is the performance evaluation, where we check to make sure that the system meets the critical parameters and that it's sufficiently reliable. And we achieve that by implementing those risk mitigations. So how do we determine if what parts of the software are new? What we need to do, we use this 4-level rating scheme. So software which is not really very novel is typically existing code that's previously been used for this purpose. And if we look at the example I talked to here, which is an autonomous undersea vehicle, things like the ballast control system and the robotics framework that it uses are existing software that's been used for similar applications before. So there's very little novelty and relatively little risk there, we anticipate. The next level is if you're talking about existing code that's used in other applications, but not in this particular application. So an example there would be the pattern recognition. Pattern recognition there's established algorithms for that, but they haven't actually been used in the way they were used in this autonomous underwater vehicle. The third level is where we have new code, but it's an existing application. We're developing new code for something that's already been done before. And an example for this might be implementing a communications protocol for the specific hardware and software configuration that we have. And then the most highest level of novelty is if we have new code and a new algorithm performing a new application. And in this system, it was intended to follow pipelines. And so the pipeline following part of that is completely new. And the idea, of course, of going through this is that we want to focus our qualification attention on the innovative aspects of the system. So what do we mean by technical risk analysis? What we do for each novel component, we need to determine how that component can fail, what are the consequences of failure, and what's the probability of failure. And then if it does fail, how big is the consequence? Is it catastrophic or just interfere with the operation a bit? And then for critical failures, we need to have mitigation actions that we develop as part of the risk analysis. And this process typically generates lots of data. It's often done in an Excel spreadsheet. The data is captured in an Excel spreadsheet where all of these things are columns in the Excel spreadsheet. And there are typically hundreds of components, maybe thousands. So there's a lot of data, and it becomes a real challenge just to manage that data that you collect and to make sense out of it and use it in the end. Another activity that we, once we've selected our standards, we need to assess whether or not we're conforming to standards. And the standards typically apply to two things. One is the process, and the other is the product. So we can use in-process audits that are based on the standards that we've selected. One that's common is the CMMI, Capability Maturity Model Integration. And another is the ISO IEC 15288 and 12207 standards. 15288 is for software engineering, and 12207 is for 15288 is for system engineering, and 12207 is for software engineering. So these are also used, and sometimes if you're in contracts, as requirements. We also typically need to do code reviews and inspections as the software is being developed. These help to determine the correctness relative to the specifications. And also we can check that whether or not we're conforming to different protocols like communications and security that we're supposed to comply with during this process. Some problems in the code can be identified through static analysis, for example, checking for memory leaks, especially if we're using C++ code. So that's another activity that needs to go on. And then once we've done that, we've actually built the system and tested it, we need to collect the data. And one thing we typically try to do is reliability analysis. This is an example of reliability analysis using an approach called the performance frontier, where the idea behind the performance frontier is that there's some theoretical optimum performance for the process. In this case, we're talking about the testing process. And we hypothesize that performance frontier has a Weibull shape, and that's based on other research that we've done in the past. So what we're really trying to do is we're trying to figure out what Weibull curve best explains the observed data, which are the pink dots. And the green line here is a comparison of the slope of the actual data, and the slope of the Weibull curve. And we expect this to be kind of on average a straight line across if we have a good fit. So this is not a regression problem, because what we're not trying to do is we're not trying to predict what's the next result when we test. That is an interesting question of how many defects will we find in the next week of testing. But what we're really trying to estimate is how many defects there are overall in the system to be found, and that's the area under the curve. So that's why we use this performance frontier approach. So that leads us to some of the possible further research topics. That's the process that we go through. And from my point of view, where we could definitely use some improvements in this process is in terms of defining the operational scenarios to better support safety analysis. There are standards for operational scenarios. In fact, I participated in developing one for the American Institute of Aeronautics and Astronautics, but it wasn't specifically focused on safety analysis. I think there's an opportunity there to develop a standard for defining operational scenarios to support safety analysis. What do we really need to know about the operations to do safety analysis? And then I think there's an opportunity to improve technical risk analysis approaches. The FAMICAs and FAMIAs, which are generally used, are, as I say, they're very labor intensive and not optimum for software. So there's an opportunity for someone to come up with some different way of doing that. And then I think there's no need for more work on alternative reliability modeling approaches. As I said, I use this performance frontier approach because the regression modeling didn't seem to me like it was going to provide the right kind of answer. It wasn't going to answer the question that I really had. So I think there's an opportunity for improving on that reliability modeling, and maybe there's other approaches too that probably would be helpful. So to summarize, safety has to be viewed from a system perspective. Understanding operations is how the system is going to operate is key to that. And you need to look very broadly for risks, not just project management risks. And then you need to monitor and update your safety analysis as the operating environment changes over the life of the system. There's a couple of references here. The first one is an article that I authored in this as a chapter in this book on perspectives on systems engineering. There's also the American Petroleum Institute provided recommended practice 17Q, which is subsea equipment qualification, which has been updated several times between 2010 and 2018. And then the version of technology qualification that I've worked with has really been the DNV approach, recommended practice A203, technology qualification, which came out originally in July 2013. When I left DNV, there was an update in progress that I contributed to. I'm not sure of the status of that. So, as I said, this is all based on experience, so I want to thank a number of organizations for providing me with experience that enabled me to do this work. One, of course, is DNV, Detmers Veritas, Hyundai Heavy Industries, Daewoo Shipbuilding and Marine Engineering, and some heavy industries also gave me opportunities to work on several offshore vessel projects. That was very helpful. And I did a lot of work with NASA on the different spacecraft. And also I spent some time at Carnegie Mellon University Software Engineering Institute, and I learned a lot there. So these are some of the experience that went into this presentation. So thanks for your attention, and I hope you have a great conference. Bye-bye.
Once again, could you take us through the work you have done so far?
So I would not say that I'm really a software safety expert per se. I'm an expert in software quality, including reliability and safety. As I try to make clear in my presentation, these things are all related to each other. They're codependent. You can't really have one without the other. And I've worked on a number of safety critical applications. At the beginning of my career, I worked on spacecraft navigation systems for NASA. And towards the end of my career, before I retired, I was working on offshore vessels and marine systems for ships that were being built in Korea. And you have, in both cases, you have a kind of a similar problem, which is that you have a device, a satellite, a blow-up preventer, or something which is going to be, that you're going to launch, and then you really just can't go and visit it and update it. You know, you can't send your IT people there to straighten things out if something goes wrong. You've got to be able to have confidence that it's going to work. And so there's these systems where you have to have a high degree of dependability are the kinds of systems I worked on for most of my career. So my experience has really been practical in terms of working on these kinds of systems and trying to make them work reliably and dependably.
The first question. Recently, routing error by the major Korean telecommunication network provider caused nationwide network service disruption for longer than an hour. This disruption has led small business owners to financial losses. Can this problem be solved from a perspective of software safety, or is it a mere human error which can occur during the operation?
Well, I don't really know enough about the specific situation to really sort of assign blame. But I would say that this kind of situation needs to be treated at two levels. One is the level of the telecom company, which needs to work to make its systems more reliable and dependable. And then the other is the level of the companies that are using the system for these critical applications. And they need to make their systems robust so that a failure of the telecommunications doesn't lead to some kind of catastrophic failure of their systems. So it needs to be approached at both levels. It's not really, you know, neither solution, neither party can really solve the problem on their own, I don't believe.
So question number two. A failure can occur not only due to software, but also due to hardware. And which failure is easier to prevent or manage in advance?
Well, it depends on, you know, one of the things with hardware failures is you can all protect against a lot of them by strategies like redundancy that are very well understood, but that don't work very well in software or are very expensive to do in software. I talk a little bit about the space shuttle example in my presentation, where there's, you know, they have 5 systems on board, 5 computers on board, 4 of which are 2 primary computers and 2 backups for those primary computers. And that's to protect the hardware. But there's another computer, the 5th computer, which has a different version of the software, and that's to provide redundancy for the software. But that means that the NASA had to pay to develop that software twice to have an independent version of the software to check with the other version of the software, because the other 4 computers are all running the exact same version of the software. So if there's a software failure on one of them, all 4 of them are going to probably fail in the same way. So that's why the 5th computer with a different version of software is necessary. So, you know, the protection against software problems can be much more expensive if you look at the traditional methods of doing it, which is like through redundancy.
Do you see that there will be more software-induced failure in the future? If then, how can the government cope with or hedge against it? And which preventive measure could be made at a state level?
Yeah, I think you know, we're in a situation where everything is becoming more connected over the internet. You know, we have this concept of the Internet of Things, so that you can get your refrigerator to talk to your computer, and your TV and all of these kinds of things and interact with them. So I think that as more things get connected, there's going to be more opportunity for these kinds of failures. And a lot of the failures are due to miscommunications about, how the communications is supposed to be handled, the communications protocol, and these kinds of things. And I think that there is a role for government in terms of kind of establishing protocols for these kinds of things, for this Internet of Things. How should communication be handled? What kind of priority scheme should be used? So I think there's a role for that in terms of establishing standards for these kinds of systems, because they're very pervasive. And of course, in Korea, the manufacturers there, like Samsung and LG, are at the leading edge of doing this kind of stuff. And I think there really is an opportunity for doing it better.
And you mean that there would be more opportunity for the government and also for the company to cooperate with each other?
Yes, I think that in general, where these kinds of problems arise is when you have different, systems that are developed by different people, different organizations, trying to communicate with each other. They make assumptions about what's going to happen, how the other system is going to receive their data, and what they're going to do with it. And unless there's some standardization, things are going to go wrong. I mean, when I started programming for the first time on a digital computer, a DEC, forget which number it was now, a DEC or a VEX, the commands, like for read a file would be something like JLG. It wouldn't be read, R-E-A-D, it would be JLG. And the reason why it would have that code was because that was the initials of the programmer who developed it. So no one, would guess that was the read command, unless you actually already knew about it and hadn't been trained. You would probably assume that it would be something like read. And so if you saw, JLG in the code, you wouldn't know what was happening. And so the thing about the computers and software is that it's really it's a virtual world. Anything is possible. That's why you have situations where, like we had these F-22s that flew across the international date line, on their way to Japan or Korea, and their control systems turned off because they weren't programmed to handle the crossing the international date line when all the dates got set back. And so they stopped flying, basically. The navigation system stopped working, and the pilots were entirely on manual for the last 1,000 miles. So, there's, assumptions are what really kill us. We make assumptions about what we expect to happen, how things will work, and we don't check those assumptions. And I think that's one of the opportunities, or one of the benefits of having some standards, is that we can kind of make the assumptions more realistic and more predictable, more accurate about what's going to happen.
So which kind of effort have been made by the Brazilian government to ensure the software safety? And do the companies recognize the importance of the software safety and put much effort on developing and operating the safe software?
I think the answer is that it varies a lot. You have some companies like Petrobras that are more forward-looking and more advanced, but then you have a lot of companies that really are not paying much attention to this issue. It's highly variable in the community there. I think the software engineering has really only taken off as a discipline and a research topic in Brazil in the last maybe 10 to 15 years. I helped to bring the concept of practical software measurement, a measurement scheme for management of projects, into Brazil. And I helped to introduce the idea of defect causal analysis into Brazil, working with the UFRJ, the University Federal do Rio de Janeiro. They're making progress, but they're in order to reach real concern and to be able to address safety, you have to address quality and reliability first. So there are ways down the curve, I think so.
To wrap up this meeting, could you leave a message or say a little word to the IT student or expert who will be participating in this conference?
Well, I think it's a wide open area. There's a lot of things that need to be done in terms of research, and certainly there's a lot of need to improve the practice of how software is developed. So there's a lot of opportunities in this field, I think, both for researchers and for students. Now, you didn't ask me about one thing that I was fairly sure you were going to ask me about, which was the reliability analysis that I presented in the example. Would you like me to expand on that a little bit?
Yes, please, if is it possible. Thank you very much.
So there's one of the slides which shows, let me get to it here. It's a reliability analysis using the concept of a performance frontier. So
yes, I remember it.
The idea of the performance frontier, this approach is part of what's called exploratory data analysis. So it's a type of a statistical analysis that doesn't use hypothesis tests, and significant tests. You don't get a p-value and so forth associated with it. But the idea is that there is some theoretical best performance of the process that you're studying. And in the real world, you don't actually perform at that level of the best performance. You perform at something less. So if you're looking at testing, which is what we're doing in that slide there, what you find is that each week you don't test at the optimum rate. Some weeks, you have a holiday, Chuseok happens or something like that. And so people don't spend as much time testing, or they encounter problems that have to be fixed. They have software or hardware problems, and until those things are fixed, they can't go on and continue testing. So they're not testing at the optimum every week. So what we were trying to do is to figure out what that optimum level of testing is, because that's going to tell us how many defects there are in the system overall. And if you use conventional regression analysis, what you're doing is you're using the actual data that you have, which in this curve is the pink line, the actual data that you have to predict the next actual data, which is interesting. You'd like to know how many defects you're going to find next week, but that's not really the question you want to answer. The question you want to answer is, how many defects do you have in the system overall to be found? And that's the area under the curve. So when you found all the defects, the number of defects corresponding to the area under the curve, then you found pretty much all the defects. So that's the way this analysis is intended to work. And there isn't a correlation coefficient and a p-value associated with a correlation coefficient like you would get if you did conventional linear regression. But it's because we're trying to discover something that we can't really see, which is this performance frontier, the limits to performance. So I think there's a lot of opportunity in terms of reliability analysis, also in terms of safety and quality and reliability. A few years ago, actually, when I was first started getting interested in software, reliability analysis was a very active area of study. It seems to have died off quite a bit now. There's not as much interest in reliability anymore. But 20 years ago or so, it was a hot topic. But there's been much less progress recently. And I think there are many new ideas that could be taken advantage of. Well, thanks a lot. I really appreciate the opportunity, and I hope everyone has a great conference.